Hello everyone, I hope the slides are visible. So today we are going to go through the week 6 previous year assignment questions and some of the questions that I decided to go through like I found from the lecture series. So in the week 6 lectures, sir has talked about first um, one thing that he talked about is different byproducts and their use in the industry, and other three lectures are about the different characterization of geomaterial. And in the three lecture we mostly talk about the mineralogical and the geotechnical characterization. So we'll take questions from that. So first question is about the HVAC. So HVAC is uh, high volume fly ash cement, right? So why this HVAC is used in the infrastructure development? So in the previous lectures, we have seen that fly ash is pozzolanic substance, right? So hence it, with small amount of water only, it can cure itself, or it can consolidate or combine together. So it is important because first is because we need in this high volume fly ash concrete, we use high content of fly ash, low water content and low portlet cement. All of these three are correct, but the why it is used is because the what industries are trying is to reduce the WIC, that is water by concrete ratio, water by concrete ratio to reduce. So to in process of doing that, what we do is we use the industrial byproducts. One of them is fly ash, which is pozzolanic. What it does is that because of its pozzolanic property, it requires less water content for curing, and hence in the cement making, or what it does is less water is utilized, and we can establish these industries in regions where there is less fresh waters, right? In coastal regions or regions in India where there is water scarcity, in those places it is a very important byproduct that can be used in the concrete industries. So all of this, that in the HVAC, high volume of fly ash is used because it utilizes low water content and low Portland cement. And remember that Portland cement is actually it's artificial made in the cement industries, and it is actually it cause lot of global warming. It is actually a CO2 emitter. जो carbon footprint होता है, the carbon footprint actually increases because of Portland cement, right? So using fly ash in the HVAC actually, what it does is it reduces the water issue. So if in any place there is less water, we can simply go ahead with using fly ash in the industry and go ahead with it. And we also reduce the usage of Portland cement, which actually has a environmental harmfulness, because it actually causes more CO2, or has high CO2 fingerprint. Another is about that which of these is used as byproduct in making concrete. So we already saw in ahead that fly ash is used, but what about silica fumes? So first we need to know that what is silica fumes. So when we make the alloys, the silicon alloys, that time silica fumes are produced when you reduce the reducing the quartz in electric furnace, right? In furnace. So when you reduce the quartz, it to make silicon alloys, what it does, it releases a lot of silica fumes. Now this silica fumes actually can be used in the concrete industry in making concrete. right? Because again, it enhances the durability of the platform that or the concrete infrastructure that is built. But one of the disadvantage of using silica fume is that it is actually, first, it is corrosive, it is harmful. Another thing is that it actually takes up a lot of water. Silica fumes, what it does is it has high surface area. Because of high surface area, it takes lot of water. So if we use lot of silica fumes in making concrete, so the ideal concentration is about 4 to 5% of silica fumes. If we use anything or silica fumes more than 4 to 5% in the concrete making, what it does, it start taking water from the concrete itself. So you are putting water to the concrete for its curing. So water helps in curing of concrete. Now, if you add a lot of silica fume to it, what it does is it takes away this water because of its high surface area, right? And hence does not let it cure, does not let it settle, and it reduces the durability. So, silica fumes can only be used in a less than 5% concentration. If they are used more than that, then it actually reduces the durability of the concrete. But yes, they it is a byproduct that can be used. Okay. Another thing that sir talked about is scrape tires. So scrape tires are used in making in road construction, making pavement, asphalt pavements, all of that. Now the reason is why. So all of these we are seeing that the byproduct, the industrial byproducts are being used in other industries, and similarly scrape tire is also used in making pavement. Now the reason, what are the qualities of scrape tires that actually are important or led to this pavement construction? First is thermal resistance. Do you think thermal resistance is a quality? Yes. Scrape tires are actually, they have high thermal resistance, they are insulators. So what happens is that if you use scrape tires in making pavement, is it actually helps with the freeze thaw. So what happens is that in regions which are cold or where there is a lot of snow, that in those regions, we what we get is we get the cracks in the pavement over time, right? So if instead of like normal concrete pavement, if we use scrape tires, what it does, because of its insulating property or thermal resistant property, it actually leads to there will be less cracks or there will be no cracks. Because when there is high sunlight, what it does, it does not uh, it does not let it shrink or expand to a large amount, right? So the freeze and thaw happen because there is expansion and shrinkage, right, of the material. But if you are using tire as an insulator, what they do is they reduces this shrinkage and expansion, and hence there will be less cracks or no cracks. Another is rutting resistance. So what is rutting resistance is that it is due to the bouncing effect. So generally the roads that we see, they don't have much of a bouncing effect, but in so for example, I'll say when we are on a highway and you are going down on a highway, this bouncing effect is actually is very important. But another thing is, on many places, what happened is that there is over time, what happened, the road actually sunk uh, from locations, and it is because that uh, because the pavement or the road does not have this rutting resistance. So using scrape tire actually enhances the bouncing property of the road and hence help in the rutting resistance of the pavement, and of course it helps with the durability as well. There are other points how scrape tires are important. Here I am just only discussing three of them now. Okay, so another industrial byproducts are glass aggregates. So in the last class we heard that dredge sediments are used for the beach nourishment, right? Similarly, these glass aggregates or the pieces of broken glass, they can be used for the artificial beach creation. So beach is what? Sand, and sand has silica, right? And glass is what? Glass is also silica. So what we do is we crush it into very fine particle, and that crushed particle can actually be used in place of sand, because again it's silica. So it actually enrich the beach and helps in the artificial beach creation. Another is fill aggregates. So similar to fly ash and silica fumes, it can also used as a filler material in road construction or in concrete industries, right? Another is filter media. So in many filtration techniques where you have to separate water from all the bad material, you can use glass aggregates as that filter media, and can actually um, it can actually purify water as well. So because I'll tell you one thing, that in many even we use quartz filter in most of the cases, and quartz is again silica, right? So in place of that we can use this simple glass aggregate as a filter media to purify or clean water. So glass aggregate, even though it's a artificial waste, it can actually be used in beach creation as a fill aggregate and as a filter media. uh, Next is about the geotechnical characterization of geomaterial. So these so which of the following is used in the geotechnical characterization? So there are a lot of points. Again, I am just taking three of them. First is void ratio. Definitely, void ratio actually determine the porosity of the material. So depending on the void ratio, it is we can determine the type of geomaterial, right? So sand has a different void ratio, silt has a different void ratio, similarly clay has a different void ratio. So void ratio is nothing but the volume of voids to total volume of solid. So we know that for finer material, the void ratio is high compared to the sand, and it determines the porosity. So it is necessary to understand the void ratio of a geomaterial. Another is collapse potential. So what is collapse potential? The formula of collapse potential is so it is the change in the void ratio with the volume, total volume, right? So it is basically used um, if you have a let's say you have a pile of landfill, right? Now collapse potential is used in that case, that after reaching what height it will collapse into the ground. Now it depends on the void ratio, which is the ratio of initial to final voids, and the volume, which is 1 upon may e naught, which is the initial voids. So collapse potential is used that if there is a material after at what sorry when it loses its shear strength, at which effective stress it it loses and it falls crumbling down to the ground. So there is one plot that is given. So this is that if you plot effective stress with the void ratio, what happen is that um, so this is the initial void ratio and it goes crumbling down. So final void sorry this is the initial void ratio, right? And when the effective stress break and this void ratio changes, right? That is the final void ratio, and this determine the collapse potential of a material or of a geomaterial. So we need to understand this as well, because again it is different for different material depending on their void ratio, depending on their total volume and effective stress. um, the collapse potential will change. Another is consolidation and compressibility. Definitely, depending on all of this, actually, if you see, it depends on the voids. So, if you have consolidation is in the case of water, right? So, the more pore you have or the more voids you have, the more water you can store, and when you consolidate it or compress it, it requires higher amount of force or energy to compress or consolidate this material, right? If you have less number of, so it requires it needs high compressibility, right? On the other hand, if the void ratio is less, it accommodates less water or less saturation, and then it requires less compression to consolidate itself. So these are all the properties that actually are used are used for the geotechnical characterization of the geomaterial. So these three. Now, these questions are the ones which are already there in the previous year assignments. So, first is about unit of collapse potential. So, we know that in the top we have what? Void ratio, no unit, and then at the down also we have 1 minus E naught, again no unit, right? So, there is collapse potential does not have a unit because void ratio does not hold a unit, right? And even though at the bottom there is, we say it's volume of the void, but it is 1 plus E naught. So E naught is number is initial void ratio, so again no unit. This is a numerical sort of question where the collapse potential is given and the final void ratio is given, and you need to define initial void ratio. So you have to find E naught where EF is given and CP is given. So let's put it into a formula. So CP is equals to E naught minus EF 1 plus E naught, right? So CP is 0.11 is equals to E naught, which is not given, minus 0.80, which is the final void ratio, 1 plus E naught. Now we solve it. So uh, you take 0.11 in the denominator and 1 plus E naught on this side. So we get 1 plus E naught is equals to E naught minus 0.80 by 0.11, and so we get point. So this is on the entire, right? So we separate it. Just a second. E naught upon my point 11 minus 0.80 upon point 11, 1 plus E naught is equals to. So what we do is we take E naught terms on one side and without E naught on other. So E naught minus E naught upon point 11 is equals to minus, if you divide 0.80 by point 11, it comes around 7.27, and then this 1 is in positive, it will go negative, and so we solve it as, so you multiply this here, so point 11 E naught minus, there is nothing in front of it, it means it's 1, so 1 E naught point 11 is equals to minus 8.27. You take it here, and on this side we got point, from 1 you minus point 11, we get 0.89 E naught, and is equals to, you take minus, this comes minus because 1, so 8 into point 11, so we cancel negative from negative, we got here 0.91 divided by 0.89. When you solve it, the answer will be 1.02. So the initial void ratio of this sandy soil is 1.02, right? So we use this formula. Now the last one is about the XRD. So XRD is nothing but X-ray diffraction diffractometer, right? So there are plots that is given in the lectures, which sir actually got from the XRD, and those plots actually, because it it is on the principle of diffraction, so those patterns are actually called diffractograms. Now another is about which of these is true about the XRD. So for that we need to know that on what principle XRD is based. So XRD is based on Bragg's law, and what Bragg's law says that n lambda is equals to this 2d sine theta, right? So it means that the light that is passing through a diffractometer, right? It depends on the the distance between the so d is the intermolecular space, right? So the wavelength of the light actually depends on the distance of the space, and this lambda is the incident angle, right? So if we know this about XRD, we know that this first point is wrong, that it is depend on Beer-Lambert law. No, it's not, because it depends on the Bragg's law. Another is about that it is not an appropriate technique to identify amorphous phase. Now, we know that there are two types of solid, right? Crystalline and amorphous. What is the difference between two is that in crystalline, there is a regular arrangement of particles or uh, of small units in a lattice, right? Uh, in amorphous, there is irregularity, right? So since I said that this Bragg's law, according to Bragg's law, XRD depends on the intermolecular distance. So, and it actually is important because it tells you about the type of material or the uh, type of mineral, let's say. So most of the mineral that are present, they are actually crystalline. You take quartz, You take feldspar, all of them are crystalline. They have a regular arrangement. This regular arrangement helps in their better analysis of XRD, and so of course it is not it cannot be used where there is irregularity or for the amorphous phase. So point B is right and point 1 is wrong, right? Another is diffraction pattern is unique to a specific material. Yes, because depending on the mineral in a material, the diffraction pattern changes. There are three plots that is given in that lecture series, and in one of them, the plots is very irregular. Like you cannot identify anything in that plot. That was about a glassy material where there is, which is actually an amorphous phase, or there is no proper arrangement. So of course, diffraction is pattern is used or is unique for one type of material. So for quartz, it is specific. For feldspar, it is specific. Now another is this formula. They have these symbol have specific connotation. No, they do not. Uh, it is it is only defined for the Bragg's law, right? So for the XRD, these two statements are wrong, and B and C statement is right. So for today, I could not find any more questions. So this is it for today. If you have any questions, you can ask me, because for today it's done. It's very early, but then I could not find any more good questions. So if no one has any questions, we can end this section here. Okay, thank you. Okay, so I'm ending this session.